For this section, we're going to talk about applications using rational equations and proportions. And just remember, in math, applications generally means word problems. And when we work with word problems, we do need to use something called direct translation. We've dealt with this quite a bit this semester. So direct translation is the process of converting words to math. Now, remember, that's a very informal definition, but it is quite literally what you're doing. Direct translation is just taking words, sentences, paragraphs, and creating expressions and equations out of that. Okay. Now, the first type of problem we're going to deal with, they're problems involving motion. And a lot of times you'll see them called uniform motion problems. And you do have to take some liberties with these problems. You do have to assume that something is moving at a constant speed, never speeds up, never slows down. There's just some uniform motion for these to be completely accurate. And there are two formulas that we need to know for motion. And the first one you really need to know. And as long as you know the first one, you can find the second one, and I'll show you how. So the first formula is that distance traveled is equal to the rate you travel multiplied by the time you travel. So if you take distance, it's going to equal rate times time. So D equals RT. Now, the second formula we have is for time, and this doesn't just poof appear from nowhere. If you have distance equals rate times time, we can easily solve this formula for R. We learned how to solve formulas. We've done that a couple of times so far. So in order to get T alone, we need to undo the multiplication of R and T. So we would divide both sides by R. On the right, R divided by R is 1. 1 times T is T. And then D divided by R is just D divided by R. So that tells me that the time I spend traveling is equal to the distance divided by the rate. So we didn't just get that time formula from nowhere. We got it by solving the distance formula for T. Okay. Now, in the first example, we're going to look at just filling in formulas. We're not going to do anything crazy yet. So I just want you to understand really what these formulas are doing. So for part A, it says, how far will you travel if you drive at a speed of 60 miles per hour for 3 hours? Well, how far is what we're looking for. That's our distance. Our rate is 60 miles per hour, and our time is 3 hours. So the distance traveled is 60 miles per hour times 3 hours. Well, units cancel, okay? So when you have something top versus bottom, we say they cancel. So hour divides into hour. So we simplify and we get 60 times 3, which is 180. And our remaining unit would be miles. So we get 180 miles. And that should make sense. If you travel 60 miles per hour at a constant speed for 3 hours, you're going to end up going a total of 180 miles. Now for part B, it says how long, so that's our time. How long will you have traveled if you drive 192 miles, that's our distance, at a rate of 55 miles per hour? So T equals 192.5 miles divided by 55 miles per hour. Okay, so this one gets a little weird with your units, but basically we're just going to take 192.5 and divide it by 55. So that's not math I care to do in my head. So let's meet at the calculator. Okay, so we take 192.5. That's the distance we travel, divided by the rate we travel, which is 55. And that tells us that we traveled a total of 3.5 miles. Or 3.5 hours. Let's go back to the worksheet. Okay, so when you do this, what happens is your miles cancel and we end up getting hours left. Don't worry too much about that, but you're going to get 3.5 hours traveled. Okay, so just know how to use those two formulas. Again, the distance formula quite literally tells you the distance traveled. The time formula quite literally tells you how long you were traveling. Okay, now I would love to tell you all of the uniform motion problems are this easy, but they're not. So let's look at example 2. So example 2 says fill in the table based on the given information. One of the issues students have with word problems is they don't know how to organize the work. This table is going to be a pivotal part of these uniform motion problems. So really learn and understand this table. So let's read the problem first, then we'll look at how this table came to be, then we'll fill in the table. So the problem that we're trying to solve, or that we're going to look at, is the river has a current of 2 miles per hour. So there's some river out there somewhere that has a current of 2 miles per hour. A motorboat takes the same amount of time. That's super duper duper important. The same amount of time. So a motorboat takes the same amount of time to go 48 miles downstream as it takes to go 36 miles upstream. What is the speed of the boat in still water? We're going to let R equal the speed of the motorboat. So when you're dealing with direct translation, you always assign a variable to what we don't know. We know the speed of the current. We know how far we traveled upstream, downstream. What we don't know is the speed of the boat. That's what we're looking for. So again, we're going to let R equal the speed of the boat. Okay, so then we come over here and we have this table. So notice that I have just distance equals rate times time. That becomes the columns of the table. You have a column for distance, a column for rate, a column for time. We then have rows for the two components of this problem. So in this problem, we have going upstream versus going downstream. Okay, so let's fill in what we can easily fill in just from the problem. What we can easily fill in is the distance traveled upstream and downstream. So upstream, we went 36 miles. Downstream, we went 48 miles. That's easy enough. Okay, now we need to use our direct translation tools to figure out the rate. Now we know that we're going to let R equal the speed of the motorboat. And when you're dealing with these uniform motion problems, you're going to have something moving. You're going to have a boat moving, a person moving, a car moving, an airplane moving. So the thing that is moving, you always start with that, and then you apply some action on that. So in this case, we're going to have the speed of the motorboat, and then we're going to see how the current impacts that speed. So we know that we have the motorboat. So we're going to start the rate for each upstream versus downstream leg of this trip with R, R being the speed of the motorboat. But how does the current impact the speed of the motorboat depending on going upstream versus downstream? Well, we know the current, first of all, is 2 miles per hour. But when we're going upstream, we're fighting the current. The current is pushing against us, slowing us down. So we would say when we're going upstream, the current is reducing the speed of the motorboat by 2 miles per hour. So it's going to make you go slower. Now, when we're going downstream, it's the opposite. The motorboat is pushing us, it's helping us, it's speeding us up. So the impact the current is going to have on the speed of the boat is going to make it go faster. So it's going to increase the speed by 2 miles per hour. So now we have this expression using direct translation for the rate that the motorboat is traveling upstream, R minus 2, versus downstream, R plus 2. So you can see the impact of the current on the speed of the thing moving. Now, as far as time is concerned, we don't have any information about time except the distance traveled upstream versus downstream happened in the same amount of time. But we also know this. We know that time is equal to distance divided by rate. So we're going to go down here and we're going to take our distance and divide it by our rate. And then you're going to use this table to create an equation. And for this class, this chapter anyway, we're going to create the table, or we're going to create the equation from the time column of the table. You either have your two times set equal to each other, like what we have here, because we know we traveled upstream and downstream in the same amount of time, or you could have a situation where you have two individual times that you add and set equal to some number. In this case, if we were going to solve this, which we don't have to, we're just asked to fill in the table, the equation that we would use, well, we know the times are equal, so I would take 36 divided by R minus 2 and set it equal to 48 divided by R plus 2. That would be the equation that we would have needed to solve. The question doesn't ask for that, though. So let's go ahead and look at example 3. So example 3, this is the true uniform motion problems. This is what I would expect you to know on a lab, a quiz, a test, homework, whatever. All right, so example 3, it says solve, include units with the final answer. So for part A, it's almost identical to the previous example. Part A, it says a boat can travel 12 kilometers down the river in the same amount of time it can travel 4 kilometers up the river. We are then told that the current is 2 kilometers per hour. And then what we're being asked is How fast can the boat travel in still water? So we've got a bunch of stuff happening here. We've got absolutely just known information underlined in black. We know the distance traveled downstream and we know the distance traveled upstream. We also know, highlighted in yellow, something really, really important. The time it takes us to go 12 miles downstream and 4 miles upstream are the same. Okay. We also have the speed of the current. We know the current, again, is 2 miles per hour. What we don't know is the speed of the boat. So we want to let x equal the speed of the boat. Or you could use r again, like we did in the previous example. So we're going to let x equal the speed of the boat. Again, you're assuming the speed of the boat in still water. So assuming you have some like giant pond, how fast could that motor boat go without any current acting on it? Now let's create our table. So we created the previous table by taking a column for distance, a column for rate, and a column for time. And then we had rows for the two components that we were looking at in the problem. So we're going to do the same thing. We need a row for upstream. We need a row for downstream. And then we want to fill in what we absolutely know. Two things we absolutely know are the distance traveled downstream and upstream. So we traveled 4 kilometers upstream and 12 kilometers downstream. Okay. We also know a little bit about the rate. We don't know the exact rate, but we do know that the rate of the boat is going to be x, and we know the current acting on the speed of the boat is 2 miles per hour, 2 kilometers per hour in this case. Okay, so you always want to start with the thing moving. What is the speed of the boat, the car, the plane, the person? Okay, and then if there's some force on that, you want to do that second. So we're going to start with the speed of the boat. Okay. And then when we're going upstream, we're fighting the current. The current is pushing us, it's slowing us down. So the impact of the current on the speed of the boat going upstream is that the current is going to reduce the speed of the boat by 2 miles per hour or 2 kilometers per hour. Okay. Now, when we're going downstream, it's the opposite. When we're going downstream, the current is pushing us along. It's speeding us up. It's increasing our speed by 2 kilometers per hour. Okay, so we've got x minus 2 going upstream and then x plus 2 going downstream. And then finally, time. We're not given any information about time other than it's the same amount of time going 4 kilometers upstream as it is to go 12 kilometers downstream. Other than that, we just have to remember that time equals distance divided by rate. So the distance traveled is 4 kilometers divided by x minus 2, or 12 kilometers divided by x plus 2. And then because we know that we're traveling 4 kilometers upstream in the same amount of time that we go 12 kilometers downstream, we want to take these and set them equal. So we're going to go 4 over x minus 2 equals 12 over x plus 2. And now when you're solving rational equations, and this is definitely a rational equation, you could multiply all terms by the LCD and then solve. Or if you're dealing with very specifically a proportion, you can just cross multiply and solve. This is a proportion. So you have to remember from the previous worksheet, a proportion is a situation where you have exactly 2 expressions equal to each other. If you have exactly 2 expressions equal to each other, you can cross multiply and solve. So we would get 4 times x plus 2 equals 12 times x minus 2, and then we just have a simple linear equation to solve. So we're going to distribute first. So 4 times x, and then plus 4 times 2, so 4x plus 8, and then 12 times x minus 12 times 2, so 12x minus 24. I want to get all of my x's together, so I'm going to subtract 12x from both sides. That's going to give me, let's see, negative 8x plus 8 equals negative 24. 12x's just become 0. I'm going to move this problem up just a bit for the sake of space. So I've got my 8x's together in a single term. I need to isolate that term now. So the issue is the plus 8. I want to subtract that from both sides. 8 minus 8 is 0, so that leaves me just negative 8x on the left. And then the right, when I simplify, let's see, negative 24 minus 8 is negative 32. And then to finally get x alone, I need to undo the multiplication of -8 and x. Well, -8 divided by itself is 1. 1 times x is x. And let's see, -32 divided by -8 is 4. Well, 4 what? Okay, you can't just leave the answer here as x equals 4. We don't remember what x is necessarily. Well, we have to go back and acknowledge that x is the speed of the boat. So x kilometers per hour is the speed of the boat in still water. So without the current acting on the boat could go 4 miles per hour. And there you have it. So that is a uniform motion problem. They are generally not students' favorite. They are a little bit more complicated. There's a lot going on. I beg you to use this table. Okay, the table is going to be a lifesaver with these problems. All right. So next up, let's talk about Joanna. So Joanna can run twice as fast as she can walk. That's very important. We need to remember that. She can run twice as fast as she could walk. So if she could walk 4 miles per hour, she can run 8 miles per hour. If she could walk 3 miles per hour, she could run 6. If she could walk 2 miles per hour, she could run 4. Okay. If she runs for 12 miles, so this is important, and walks for 8 miles, okay, we know she's running for 12, walking for 8. The total time to complete the trip is 5 hours. So we're going to have some amount of time spent running, some different amount of time spent walking. And if we add those 2 times, the total trip is going to be 5 hours. So keep that in mind. And then the question that we actually need to solve is to the nearest tenth, how many hours did Joanna run? Okay, so we got a lot going on here, but we also have a lot of information. The first thing we need to do is assign a variable. We have no idea how fast Joanna walks or runs. We know she runs twice as fast as she walks, so we have no information about her running speed. So we're going to let x equal her speed walking. Okay, so SPD for speed walking. And then now let's create our table. So we know we want a column for distance, a column for rate, and a column for time. And then we need a row for walking and a row for running. And again, I cannot encourage you enough. I'm begging you to use this table. It helps you organize your thoughts. Okay. Now we know 2 things. We know how far she's going to run and how far she's going to walk. So she's going to walk 8 miles. She is going to run 12 miles. We also know her rate of speed walking. We know she can walk X miles per hour. Okay. Now, if she walks X miles per hour, we know she can run twice as fast. So to figure out twice as fast, you just multiply her walking speed by 2. So in order to find the time, we're not given a lot of information about the time, but we know if we add the 2 times, it's going to equal 5 hours. So we need to find the individual algebraic time spent walking and then running, add them, and set it equal to 5. And that'll give us our equation to solve. So let's see here. Joanna can go 8 miles per hour, or she can go 8 miles at a rate of X miles per hour. So her time is going to be distance divided by rate. We know she can go 12 miles at 2x miles per hour. So that's going to be 12 divided by 2x. And we want to take those 2 individual times. We don't know how much time each of these are, but we know the individual times are going to be 8 over x, 12 divided by 2x. And if we add those and set them equal to 5, we can solve for x. So we've got 8 over x plus 12 over 2x equals 5. And this is a regular old rational equation, so we need an LCD. In this case, our LCD is 2x. Now, if you wanted to, you could just simplify the 12 over 2x. And if you did that, the LCD would just be x. That's fine if you see that little trick. If not, we're just going to do it this way. So we want to take our LCD and multiply it by both terms on the left and the one term on the right. So we multiply basically everything by the LCD of 2x. We want to simplify out our denominator, so all of our denominators are going to divide out. So I know that the LCD of 2x divided by the denominator of x, so the x's divide out to be 1. So let's see, that leaves me with 2 times 1 times 8 for the first term. So 2 times 1 is 2, 2 times 8 is 16. So my first term simplifies to just plain old 16. For my second term, 2x in the denominator divided by 2x into the LCD is just 1. So 1 times 12 is 12. So my second term simplifies to plain old 12. And then my third term is just 2x times 5, which is 10x. So let's see. On the left, I get 16 plus 12 is 28. So 28 divided by, or 28 equals 10x. And in order to get the x and the 10 separated, to get the x alone, I would divide both sides by 10. Well, 10 divided by 10 is 1. 1 times x is x. And then 28 divided by 10 is 2.8. But we have to go back and be like, okay, x is what? What does x mean? Well, x is the speed walking. So x is 2.8 miles per hour walking. We then have to ask ourselves, does that answer the question that we were being asked? And in this case, no. The question that we were being asked is, how many hours did Joanna run? Well, we have to figure out a couple of things here. We can, one, figure out the rate and then divide it by the distance, or we can just use the time formula, plugging in 2.8 for x. So notice here, let's circle it in green. We have the time spent running is 12 divided by 2x. So if we take that little piece, the 12 divided by 2x, that gives us the time that Joanna spent running, and we know that x is now 2.8. So let's see. We have 12 divided by 2 times 2.8, which is, let's go to the calculator. So we have 12 divided by 2 times x, but remember x was 2.8. Hit enter. And we're going to round to the nearest tenth, I believe it said. So this would round to 2.1. Okay. So we can then say that this is equal to approximately, we're going to use a little squiggly equals for approximately equal to 2.1 hours. So again, if we solve this, we're solving and we find x, which is the speed that Joanna was walking, but we use that x to figure out the number of hours Joanna spent running. So 2.1 hours running. And that's kind of a cheap explanation, but for the sake of time, we're going to leave it at that. So Joanna spent approximately 2.1 hours running. All right. So these are not necessarily the easiest problems out there, but they are manageable. I highly, highly encourage you to create this table. For this class, we're only going to look at 2 scenarios. A scenario where you have 2 times that need to be set equal, or 2 times that you add and set equal to another number. So these are the only 2 scenarios I'm going to test you on for this chapter.